So before going to some rank 2 update methods, we will look at theorem 3.2.1, which shows or writes some interesting properties of this rank 1 update method. So it says that if three conditions hold, number one, if all iterates are well defined, that means the denominator that we talked about is non-zero always, and delta 1 to delta n are independent, so recall that these deltas are the differences in x values. So we are assuming that these vectors are linearly independent, and if my original function f is quadratic. So then what this theorem says is a rank 1 method will terminate in n plus 1 searches exactly, or sometimes even less, okay, but never more than n plus 1 searches. The proof of this theorem is not too complicated, and you can try to understand it yourself. But it says that at least when function f is quadratic, I have finite convergence. It's not that I will converge only in the limit. When f is quadratic and the Hessian is positive definite, it must converge in n plus 1 searches. So that means already this method is better than steepest descent, because steepest descent may only converge in the limit and not really in infinitely many steps. So this proof is somewhat important, because similar proof can be used for later better methods. So what about Newton's method for the above function? In contrast, steepest descent may take far more steps. And what about Newton's method? Newton's method actually may take only one step, and it will converge, okay, given these assumptions, right? In fact, only condition C, that f is a quadratic and Hessian is positive definite, then if I just take the Hessian inverse and choose the direction, then in one step you can show that you will hit the optimal. In fact, you can find the closed form solution also of the optimal when f is just a quadratic function. So we will not go into the details of the proof, but please do read it and try to do it on paper yourself after reading it. Okay, so now let's come to rank 2 updates. and here we would like to update hk plus 1 as hk plus a rank 1 matrix multiplied by scalar a, and one more rank 1 matrix with scalar multiple b. Okay, so a and b are some scalars that we want to pick, and UU transpose is a matrix of size n cross n, so that we can add it to HK. Okay, so now it is called a rank 2 update because these are both rank 1 matrices. So again, I want the Quasi-Newton condition to hold. That means my delta k has to be equal to hk times hk plus 1 gamma k. So that means if I substitute hk plus 1 as hk plus a UU transpose gamma k plus b VV transpose gamma k, and we would like to decide a and b. So again we notice that u times gamma k is a scalar and v times gamma k is also a scalar. So which means that if I look at this sum, that sum is equal to delta k minus hk gamma k. So if we pick this a times u to be parallel to delta k and this to be parallel to hk gamma k, then hopefully I'll be able to add these terms together and check whether Quasi-Newton condition is holding or not. Okay, so as an exercise, you can substitute this U transpose gamma k to be delta k and V transpose gamma k to be HKVK HK gamma k, and then you can try to find out the other values, unknown values. So this gives us a very nice expression for hk plus 1. Trying to show that hk plus 1 is what we are trying to get. You can try to do it as part of your assignment to prove that the formula that we are writing is correct. So hk plus delta delta transpose upon delta transpose gamma minus H gamma gamma transpose H gamma transpose H gamma. So verify that this is a scalar, this is also a scalar, and this one is a rank 1 term, and this is also a rank 1 term because I am multiplying a vector by its transpose. So similar to UU transpose that we did earlier, you can show that this is a rank 1 matrix, this is also a rank 1 matrix, both are positive definite, but since I have a negative here term, then I can't be very sure that everything is fine. I still have to make sure that H is positive definite and HK plus 1 is positive definite. Okay, so we need to show that that equation 2 here is the equation. So to show the condition above is positive definite, so that we get a descent direction, I need to do two things. One is show that H minus H gamma transpose H upon gamma transpose H gamma is positive definite given H is positive definite. Okay, and this is not too difficult. This can be shown using this is already shown in the book as a theorem. We will not go into the steps of this theorem, but you can try to verify it yourself. And if this term is positive definite, and in addition we have another term here, so this delta gamma has to be more than 0 because of the way we are searching. This is the change in x's, this is the change in the gradients. So so that's it about this H. You can verify that this H is having only a rank 1 update, rank 2 updates, because this is also rank 1, this is also rank 1, and you can easily also verify that this is positive definite. So this method is called DFP. Okay, so Davidon Fletcher, which is our favorite nonlinear optimizer, and Powell, another very influential nonlinear optimization researcher who made great contributions to this field. So together, independently, these three people came up with these types of updates, So this method is called DFP. And it has these nice properties that we are able to keep our H matrix positive definite, assuming that the first H guess is positive definite. So usually H1 should be positive definite and a good estimate of G1 inverse, but it's okay to pick H1 as identity, and sooner or later, because of my previous theorem and previous result, this will start becoming closer and closer to the actual inverse of the Hessian of the function. Okay, so again, this method is great in the sense that DFP is globally converging and this comes in the book, not as a proof, because Fletcher proves the results for all these methods in one go, because they are all interrelated later, but what is known is that DFP is globally converging and superlinear convergence. So it is better than steepest descent, and also it is better than Newton in the sense that it is globally converging as compared to Newton's method, which doesn't converge always. Also, if f is quadratic, it takes n steps to stop, at most n steps. So that means it is doing a good job of converging. In fact, one can show that Hn plus 1 is equal to G inverse if f is quadratic. Which means that for quadratic function in n steps at most, H will reach exactly same as G inverse. Okay, this result holds only for quadratic functions, not for other functions. Okay, so close to DFP method is the BFGS method, which is also a rank 2 update method and quite popular, and that we will study in the next class. So with that we will stop and see you later.